Okay, so we're going to talk about slope. We're going to talk about slope of lines. So you can think of slope as any time you have a line or even a physical object that does not go perfectly flat. It has some steepness to it, such as this skateboarder and his ramp. He has steepness to it. Okay, so that's slope. We're going to talk about how to measure it. What does it mean? We'll first talk about how to find it, given any scenario, and then we'll talk about when you're looking at a situation or a graph of a situation, how to interpret that slope into what it means. That's something I want you to pay a lot of attention to, how we interpret the slope in context of the question. Okay, in this example, this is just a skier going down, but I want you to think of, look at the definition. The slope of a line describes its steepness. How steep is it? Okay, and it's determined by its vertical change, or we can call it rise. Sometimes though, that vertical change can be going down, whereas from left to right, this one is going up. From left to right, this line goes up. Now, so we look at its steepness is determined by its vertical change and its horizontal change. We refer to the vertical change as rise, and we refer to the horizontal change as run. Now, anytime you have a line left to right, if the line goes upward, such as that one, notice this line going from left to right, it goes up, therefore it has a positive slope. The opposite of that, if a line goes downward from left to right, that line is going to have a negative slope. So slope can be positive or negative. Now, two lines have the same slope are parallel. Meaning, if they have the same slope, that means an example of that would be the lines of this gymnast's parallel bars. You see the line of that bar, you see the line of that bar. Well, those bars never cross because they have the same steepness, they have the same slope. And because of that, we know that parallel lines never cross, therefore they have the same slope. Horizontal lines, lines that go flat, like the horizon where the sun goes up and down, horizontal lines have a slope of 0, meaning a horizontal line that goes left and right, it does not go up at all. It has no steepness. Because it has no steepness, it has no slope. So we say that it has a slope of 0 for horizontal lines. Now, vertical lines. Vertical lines have an undefined slope. We say that vertical lines have an undefined slope because they go just vertical. Remember, vertical is up and down. They go just up and down. They never go side to side. Therefore, they can't have steepness if you never have any run. You never have any horizontal change. Whereas if you're walking off a cliff and you just fall off, you never had a chance to slide down or to go diagonal. You only went straight vertical drop. Therefore, vertical lines have we can't even talk about slope. It's an undefined slope. Simply because there's no left-right change when you have a vertical line that goes straight up and down. Now, in general, when we measure slope or we determine slope, it's always going to be measured by vertical change, which is going to be your change in y, because remember, the y-axis measures vertical. So your vertical change, or change in y, or we call it run, over the horizontal change, or the change in x. These are words we use when we're talking about constants of change. So for example, anytime you want to know the change in y, you can just look at what happens to the y values, either on the y-axis or in the y-coordinates. Or just think of it as up and down, or just think of it as vertical. So look at this hill that this moving truck is going up. The hill is going to be the rise. And then how long the hill is, that's the run. So we can think of that as rise over run. That's sometimes an oversimplified way of describing slope. We don't like to always call it rise over run, but if we at least call it maybe vertical change over horizontal change, that's a bit more clear sometimes. We're just talking about a physical object. Now, for example, a wheelchair ramp. If you were to find the slope of it, we just learned that the slope of a wheelchair ramp is the rise, so 2 over the run, or the vertical change. 2 is positive because it goes up, over the horizontal change. In this case, 8 feet. So it's going to be 2 feet over 8 feet. 2 feet over 8 feet, well, that simplifies to 1/4, 1 over 4. So the slope of this line is 1 over 4, or excuse me, the slope of this wheelchair ramp is 1 over 4. Now, if you're looking at the graph of a line, you can also find the slope of that line by picking 2 points. So for this line, we could find the slope. So pick 2 points that it goes through. You'll notice it goes through that point, the one that's popping up, okay, and the location of that point is -2, -1. It also goes through that point. If you look right there, it goes through that one, so that's another one we're going to use. And that point is 2, 2. So using those 2 points, we can find the slope of this line by counting the vertical change. So remember, it's rise over run, so vertical change over horizontal change. So up and down, this line, does it go up or down? This line goes up from left to right. So we can count. So let's see, it goes up 3 times. And now going over, its run goes over 4 times. So that means it goes up 3 over 4. So you have vertical change of 3 over your horizontal change of 4. That fraction does not simplify, therefore the slope of your line is 3 over 4. There's also a formula that you can use when looking for slope. You can use what we call the slope formula. This formula can be used anytime you're given ordered pairs, such as you have a location here, a location here. Pretend this line goes perfectly through that spot. It should be. It looks like it's moved a little bit. Pretend it goes where it's supposed to. So when you have your ordered pairs, you can now organize them and put them into what's called the slope formula. Meaning, you can calculate what is the change in y. Meaning, this is where it started, this is where it ended up. So if you do where it ended up minus where it started, it'll tell you how much it went up. So y2 minus y1. The point, remember, all ordered pairs, by the way, all ordered pairs are x comma y. We're just calling this one x2 and y2 because that's our second point. It's furthest to the right, so it's our second point. Whereas this one is furthest to the left, so it's our first point, so it's x1 and y1. So if you do y2 minus y1, that'll tell you the vertical change or the rise. Now we also need to find the horizontal change. It goes from this x coordinate, in this case -2, all the way up to this x coordinate, which is +2. So that's just giving you an explanation of what we just calculated in that last question. You could have plugged these in using the slope formula. So let's do it using those points we just identified. These are the same points from that last example from right here. 2, 2, and -2, -1. So let's see. The one furthest to the left is -2, -1. You know that because -2 is your x coordinate, which measures left to right. And if we looked at the points, this one was further to the left. So just plug them in. y2 is 2, y1 is -1. So it's going to be 2 minus -1. It's always supposed to be a minus sign right here. But when you minus a negative, what happens? When you minus a negative, remember, it becomes adding a positive. When you minus a negative, it becomes adding a positive. Because the formula says minus. But if y1 is already negative, it becomes adding. Same thing on the bottom. If x1 was already negative, it becomes adding. So the top becomes 2 plus 1, the bottom becomes 2 plus 2. So that gives you 3 over 4. But that's the same thing that we calculated before. So that agrees with the slope of the line that we found all on our own. Alright, so let's take a look at this example. In this example, we have no graph. It just says find the slope of a line passing through the following points by finding the change in y and the change of x. Because remember, the change in y is what goes on top. The change in x is what goes on bottom. This is just like what we were talking about with change in output on top and change in input on the bottom. We were talking about constant rates of change. So out of these 2 points, we want to identify the one that's furthest to the left. The one that's furthest to the left, you find out by looking at the x value. This x value is -3, whereas this one is +3. So the -3 is clearly further to the left on the xy graph. So that's going to be x1, y1. So plug them in. So you have y2 minus y1. Well, y2 is -2. y1 is +3, so you have -2 minus 3. Now on the bottom, you have x2 minus x1. That'll tell you your change in x. It went from -3 up to +3. So if you thought of that yourself, you might think, okay, well that means it moves 6 times. Or you might say, well, if I do +3 minus -3, it becomes 3 plus 3. 3 plus 3. So that tells you the horizontal change is going to be 6. Now you'll notice the top went from -2 minus 3 to -2 plus -3. That's a preference. Here in class, we mostly leave it the way it is because we say -2 means start in the negatives, minus means go left, which means go deeper into the negatives. So if you're at -2 and you minus 3, you go deeper into the negatives, so you get -5. Some people think of it this way. We don't prefer this rule method in class, but just whatever works for you in terms of adding, subtracting negatives. Regardless, they both equal -5 up top, even if you had left that as -2 minus 3. So -5 over +6, that fraction does not simplify, so that fraction is your slope. That fraction is -5 over 6. It's a negative slope, so that means our line goes downwards from left to right. And now let's look at that example of the visual to help you see it visually. Same example, same exact example. So we have -3, 3. We're going to go ahead and put a point there because it's on our line. We have 3, -2, put a point there. And you see the line that goes through them goes right here. So if you want to graph those 2 points, maybe do it visually. We clearly see it goes down. And it goes down a grand total of 5 times. And it goes over a grand total of 6 times. So the slope is -5 over 6. So visually, that same problem made sense just by counting on the graph. Now remember, when you count on the graph like this, it's exactly what we talked about last class when we were discussing constant rates of change when looking at graphs. So now you've had an opportunity to look at the slope of lines, how to calculate it, and how to find it. But now we're going to do a few examples where we not only find it, we also interpret it and talk about what does it mean. What does a slope mean in the context of a question? Here, there was no context. It was just X and Y and have numbers. There were no examples of, well, what if we were measuring how many bicycle seats you could make down, or excuse me, how many bicycle seats you could make on the Y-axis and how much time it took on the X-axis. Like, we don't actually have a scenario. That's what we're going to do now. We're going to do some applied problems. All right, we're going to take a look at question number 2 on this page. Question number 2 is what we're going to take a look at. Oop, didn't mean to move it. So on question number 2, all right. So as you read through the instructions would say something along the lines of graph it. The instructions say to draw the graph and find the slope and explain what the slope represents. So draw the graph, find the slope, and explain what the slope means. That's what we're doing. Okay. All right, so now, in this question, let's start by just plotting our points. This is going to use your basic skills that you learned with graphing ordered pairs. So the first ordered pair for the first one, so temperature of 70 and people of 24. So the temperature, you'll notice, is on the horizontal axis, which implies the temperature is our input, or it's our cause, meaning the temperature of the beach causes how many people show up. And if you think about it, that kind of makes sense. The colder it is, the less people want to be at the beach. The hotter it is, the more people want to go to the beach, unless it gets way too hot. But we're not going to worry about those extreme situations. So it kind of makes sense. The number of people on the beach are a result of how nice is the weather outside. So the weather is going to be our input, and the number of people are going to be our output. So 70, 24, that's our first one. 70, 24. I'm not going to write the order pairs for all of them, just want to remind you can. So find 70, go up to 24. This is 20, that's 30, that's 25, so a little less than half. So about right there, a little less than half. It's okay to round when you're putting these in there, it's okay to estimate. Now, 78, 40. So go to 78, go up to 40. Okay, that one's right on the dot, right there. 86, 56. So go to 86, go up to 56. Here's 55, so it's a little bit past halfway, so about right there. Okay, and now 94, 72. Go to 94, go up to 72, so a little past 70. About right there. Now, if you look at those dots, I actually estimated all of them, but if you notice, I did a pretty good job. Those dots are in a pretty good straight line. So draw yourself a line that goes through them. Draw a line that goes through them. You can use a ruler, you can use another pencil, a straight edge, a book, a piece of paper, whatever works for you. Just do your best to draw it carefully. I did that one with my hand. So we now have the graph of this table. So we have graphed this. We have graphed this situation. We've graphed this scenario. We've graphed these points. But now, the question said, find the slope. That's what the question said. It said, find the slope. That is our job. And then it said, find out what it means. So to find the slope, we learned that during that PowerPoint presentation, that slope is usually explained by using a lowercase m. We learned there was a slope formula that we could use. The slope formula we learned we could use was y2 minus y1 over x2 minus x1. That's one of the things we learned. So we could use that formula, and we could use two of these ordered pairs. Use that ordered pair, use that ordered pair, or use the first one and maybe the third one. We have the choice. We don't have to just use the first two or the last two. We could pick any two we want. So that's kind of what we're going to do. But we don't have to use that formula. You can also do these intuitively. Think about what we learned in class last class when we were talking about constant rates of change. We talked about putting the change in the output over the change in the input, or we said the change in the y. So change in y over change in x. We talked about putting the change over the change, except it's always the change of the output over change in the input, or y over x, or vertical over horizontal, because that's what this is really finding. This is calculating that concept that we're talking about. So that's the more intuitive way to think of this. So choose any two gaps. You can choose the gap between these two, the gap between these two, the gap between these two, these two, these two. I think that's most of the options. So it really doesn't matter. Choose any gap. So to show you that it always works, I'll choose the second one and the last one. So I'm going to find the gap between these. If you look at our x, or our input, or just our horizontal axis, which is temperature, to get from 78 to 94, alright, to get from 78 to 94, it means it clearly went up. We just have to figure out how much did it go up. We find out how much it went up by doing 94 minus 78. We subtract that, and that will tell us how much it went up. Now, so that would give us our change in y. We now want to know, oh, did I do that backwards? Let's see, temperature is our x. Yep, that one's upside down. So that's change in x that I just did. So let's flip that to the bottom. 94 minus 78. Sorry for those of you following along and you're writing that down. Remember to press pause, by the way, to try these questions before just watching them. So that was our x up top. I'll actually write it so I don't forget. Because temperature is our horizontal axis, so that makes it our x. So that's our change in x on the bottom. Now our change in y is going to be the number of people on the beach. So it goes from 40 to 72. So if we do 72 minus 40, that'll tell us how many people showed up between those two temperatures for that gap, that interval. So find out what that equals. 72 minus 40, well that's 32. 94 minus 78, let's see, that's going to be, I believe, 16. So that's going to be 16, okay? So now simplify that fraction if possible, but before you do, let's write our units of measure. So our change in y, that was the number of people. So I'm going to put 32 people. And the 16, well, that was degrees Fahrenheit. So I'm just put degrees Fahrenheit. That's what happened. 32 people increased after a 16-degree increase in temperature. So let's simplify that. 32 over 16, well, 32 over 16, that simplifies. 16 goes into both, so that turns into 2 over 1. So 2 people for every 1 degree Fahrenheit. So that's actually our rate. That's our constant rate of change we learned about last class. So when we talked about how to interpret it last class, it's the same thing now. The slope of this line, if you just wanted to find the slope, you would just say m equals 2 over 1. That's the slope. But when it asks us to interpret it, that's what we can do. When we go to interpret it, we can now say, well, okay, let's actually say what that means, which is what we learned last class. We would say 2 people showed up at the beach, or came or arrived. So 2 people showed up on beach for every 1 degree Fahrenheit increase in temperature. That's how we could fully interpret this slope into words. Meaning, every time temperature went up by 1, 2 people showed up. That's what this tells us, based on the information we're given. Now, of course, we're ignoring those extreme situations. Like, what if it was 130 degrees outside? Nobody's going to be outside in the sun at the beach. Barely anybody. We're ignoring the extreme situations. So this was an example of, we graphed these points. We found the slope through these points by using the table to help us. Because our dots were estimated dots on here, it would not do us very good to try to count how far it went up, how far it went over. It would not be a good idea to try to do that because these dots are estimated. Unless you had clear values next to them, it's not going to help you very easily. You could have used the slope formula. We did it using what we talked about with change in the output over change in the input. And some of you that might be thinking who like the slope formula method, you may say, hey, wait a minute. If we had used these two locations as ordered pairs, if we had said 78, 40, and if we had said 94, 72, the slope formula would have been 72 minus 40 on top, because that would have been y2 minus y1. Well, hey, look what we wrote. y2 minus y1. We wrote 72 minus 40. So our intuitive way of doing that, that is the slope formula. The whole change in output over change in input, it is the slope formula. They just make it sound fancier than it really is. So on the bottom, we would have done x2 minus x1. Well, this is x2. This is x1, so 94 minus 78 would have given us our change in our horizontal, which look, 94 minus 78, so our change in horizontal. So I want you guys to know this intuitive way that we talked about it, change in output or change in y over change in x, it is the slope formula. Take a moment to think about this equation and think about how our interpretation worked out. As a brief reminder, when you're thinking of slope, you're thinking of this constant rate of change. Remember that the same thing, unit rate, constant rate of change, stuff like that, it means the same thing. And later you'll learn it also means the same thing as constant of variation, but we'll talk about that later in chapter 5. Slope is the rate of change between any 2 points on a line. It can be thought of as change in y over change in x. It can be thought of as vertical change over horizontal change. It can be thought of rise over run. It can be thought of output change or change in output. So output change over input change. All these things all mean the same thing. Whatever you need to think of it as, think of it however you need to in order to understand, to interpret it, and use it. So we'll do probably one, maybe two more examples. Okay, we're going to talk about question number 1 on this page. We're going to ignore question number 2 for now. We're just going to focus on question number 1. So I'm going to scratch it out so it's not even, don't even let it bother you. Okay, question number 1, because this is a good question where we calculate a few things and we interpret them in terms of what they mean for this scenario. So the instruction says it's about go-karts. And the question says, the graph shows the average speed of 2 go-karts in a race. What does the point 2, 20 represent on the graph? What does the point 1, 12 represent on the graph? And what does the slope of each line represent? And which car is traveling faster? So here's what they want us to do. Let's first talk about what's going on here, and we'll see if we can kind of explain what different things mean. So let's look at the graph first. You see our horizontal axis, our x, well, that's time. And so if that makes sense, you choose how long you want to keep driving, you choose how long you want to keep racing, you choose how much time you're going to spend. So that's going to be your input. That's going to be the one you have choice over. So think of it that way. Time, you choose how long you're going to keep driving. Distance, which is your output, which makes it your y, but also because it goes up and down, so that's why it's the y. That's your output. That is a result of how fast you're going, and it's a result of how long are you going that fast. And notice, they said average speed. That means we're not going to get hyper technical and say, what about when you slow down for turns and stuff like that? We're going to keep it simple. We're going to say average speed. Because average speed is just overall, you went 2 miles and it took you 1 hour, so that means you went 2 miles per hour. That was your average. Even though you may have gone, stopped, like red lights and stuff like that. Okay, so go-karts. So let's see. After 1 hour, cart X, after 1 hour, cart X, you notice is that top line. So cart X, after 1 hour, has gone a little bit more than 10, not quite 15, so it looks like 12 or 13. And in fact, looking at the question, it's probably going to be 12, 1, 12. So cart X, I'm going to trace them in blue. Cart X has, after 1 hour, has gone 12 miles because it says it's measured in miles over here. So cart X has gone 12 miles after 1 hour. Okay, so in fact, that's actually what we just interpreted this point when they said, what does the point 1 comma 12 mean? It means 1 comma 12, 1 comma 12, go up 12. That means 1 hour has gone by, and cart X has gone 12 miles because because 1 is hours, 12 is miles. So that means 1 hour is 12 miles. That's what that point means. So after doing that one, I think we can figure out this one. 2 comma 20, so that's going to be for the cart Y, the one that's going to be traced in green, cart Y. So cart Y at 2 comma 20, that means 2 means 2, which means 2 hours, comma 20 means go up 20, so right here. And so that tells us we went 2 hours and we went a grand total of 20 miles, which tells us that cart, after 2 hours of driving, he has gone 20 miles. So we've interpreted this one as well. So in fact, let's write those down real fast. Let's see if we can interpret them. So 2 comma 20, that means hours, miles. That's what that tells us. That tells us we drove for 2 hours and we went 20 miles. So that almost gives you a rate, guys. That means your rate would be 20 miles in 2 hours. Now, I didn't turn that into a unit rate. I just turned it into a regular rate. So that means 20 miles in 2 hours. We can actually do that. And now for cart Y, that was cart Y, 2 comma 20. So now for the 1 comma 12, that's for cart X. So 1 comma 12, I'm using green, that was for cart Y. Let's see, I'll use blue. 1 comma 12, that means 1 hour, that means 12 miles. So that means the rate would be 12 miles in 1 hour. Well, hey, that's a rate, but that's also a unit rate. And if you remember what we talked about with finding constant rates of change, the unit rate, the constant rate of change, they're all the same thing. And so that might mean something. We'll make that connection in a moment. We'll see how that goes. So far we've interpreted 2 comma 20 and 1 comma 12. We now know what they mean. They asked for us to also, they said, what does the slope of each line represent? Well, it would help if we knew what the slope of each line was. I think that would help us. So let's see if we can find the slope of each line. So I'm going to start with cart X. If you watch cart X's line, I just erased his blue because I'm trying to trace over him. Cart X, if you look at him, doesn't quite fall on any of these points perfectly, but they do tell us what that point is. They told us that point was 1 comma 12, right there for cart X. And then this one, we don't really know what it is, nor do we really know what that one is. We don't really know what exactly point that is. We can take a guess. Looks like it might be about 36 miles. Not really sure. But you'll notice, we can use the point where they started. They both come from the origin. So we're welcome to use that point if we want to calculate the slope that way. So for cart X, so for that top line, that's what we're going to do. We're going to say, let's start here. So from here, to get to the first point, that's at 1 comma 12, we have to go over 1 mile. So our run, or our horizontal change, this is for cart X. So let's see, cart X slope. We go over 1 hour, so that means our horizontal change, our change in input is going to be 1 hour. And to get up to it, we go up 5, we go up 10, we go up a little bit more. We found out we go up 12. So that means our vertical change, our change in output was 12 miles. So, and you'll be like, hey, that looks very similar to this. Well, yeah, we just did the same thing. Because it comes from the origin, yes, they are the exact same thing because it came from the origin. Meaning at 0 hours, he'd gone 0 distance because he hadn't had time to drive anywhere yet. So that's our slope, 12 miles in 1 hour. That means 12 miles for every 1 hour, 12 miles per hour. Well, hey, that's a speed. So that means that's a unit measure we're used to looking at, 12 miles per hour, like in the speedometer of a car. So now let's talk about cart Y. Cart Y slope. We're gonna do the same thing for cart Y. For cart Y, we can see that one is right at 1 comma 10. That dot is right on the dot. That point is, this line goes right through 1, 10. So cart Y is at 1, 10 here. And if we look here, that one's also right on the dot as well. That's 2, 20. So that means if we use those 2 points for cart Y, if we use this point and this point, the change in output, or the vertical change, goes from 10 miles to 20 miles. So that means he went up 10 miles. To go from 10 to 20, he went up 10 miles. And his change in input, or his change in X, he went from 1 hour to 2 hours. Well, that's a change of 1 hour. So that fraction, that's 10 miles in 1 hour. So that's 10 miles per hour. Well, hey, that's already a unit rate. That's already the slope of the line, because the slope of the line is just a simplified fraction. That is simplified. So that's 10 miles per hour. And if you look up here, what we said up here, 20 miles in 2 hours, that was a rate. If we had simplified that rate into a unit rate, we would have gotten 10 miles in 1 hour, just like over here. So now the slope of each line, represents the speed of the go-kart, if you didn't realize that already. The slope of each line represents the speed. 12 miles per hour was the slope, because we know that because we interpreted the slope, because it was 12 miles on top, 1 hour on bottom. So like we talked about constant rates of change, 12 miles per hour. Then it says which car is traveling faster. Or at this point, you can clearly tell car X, his speed is higher. But if you also look at what car X accomplishes in 3 hours, car X goes further. He goes about 36 miles, where cart Y only goes about 30 miles. So cart X must have been going faster, because in the same amount of time, he went further. So at this point, we've answered all aspects of this question, to where we had to interpret the graph, calculate some items, but most importantly, we interpreted what the slope means. The slope of this line in this case was the speed of the go-karts. So remember, when you're working on slope, guys, be careful on how to calculate it. You can do it exactly like how we did constant rates of change, when we did change in output on top, change in input on bottom, or you can do it as change in Y over change in X, whatever you want to call it. You can use the slope formula, you can do it intuitively, you can count on the graph like sometimes we can do if these points were more clear. You've got options. So just remember, calculate your slope just like constant rate of change, and then interpret it just like constant rate of change. So practice these problems and make sure you have an idea